Hello, hello. For this week's Fiddler, I have a pretty short video for you. Not because it's an easy puzzle. In fact, I think it's a kind of strange and hard puzzle, but because I really don't have that much interesting to say about it. I don't think I did a very good job of finding some type of tractable, analytical way of figuring out exactly what to do here. But I have a couple of thoughts that I think are worth sharing. And if you have solved this puzzle, if you can solve this puzzle in a more elegant way, I am very, very interested to hear your thoughts. So here's the puzzle. You're playing a game of cards with a friend. And for the basic version of the question, there are four different types of cards labeled one to four. And we're going to take turns playing a card. And at some point, if I play a card that satisfies this strange criteria, which I'll describe in a second, you slap the cards, and whoever slaps first kind of wins. And the question is, how large can that pile get before we definitely have to slap? In other words, what's the largest possible pile I could make before a slap would be allowed? And the condition for slapping is that when I put down a card, it and some number of cards, which could be zero, right? So it and the next, we'll call it X cards, sum to the same value as the next Y cards in the pile. So some examples I think are useful here. So if you play a one and then I play a one, we could slap because the one I put down, well, if you think about it by itself, it sums to one, and the card before it also summed to one, so I could slap that. If it were one, then two, I could also slap the pile on that second two, because that two is the same sum as the card right before it, which is also two, so I can slap. If the order were one, then three, then four, I could also slap because four is the sum of three and one, and I wouldn't slap before that point. Or if the cards were two, then four, then one, then four, then three, I wouldn't slap until I get to the three. The reason I can slap in the three is because three plus four is seven, and the preceding cards I can also make sum to seven, one plus four plus two. So that's the game. So how large can we get this? So I always think it's useful when thinking about questions like this to reduce the problem into an easier version of it with maybe fewer elements or in some way kind of lower the dimension of the puzzle. So let's just think about it with two cards, right? We have a one and a two. The best I can do is three. So why can I get three cards in this chain? Well, I can't repeat the same digit twice, right? So I can't have a one followed by a one at any point, and a two can't be followed by a two at any point. So I have to alternate between one and two. But if I alternate back and forth twice, then on the second version of that alternation, I can slap because the second two in the chain will equal the first two in the chain. And it doesn't matter which order. If I go one, two, one, two, I get two sets of three. I can slap. If I go two, one, two, one, I also get two sets of three, and I can slap. So the best I can do is right before that slap, one, then two, then one. What if I have three cards? So now ones and twos and threes are all in the deck. So I still have this property that I can't repeat the same card twice in a row, but now I have to think about other things like adding up to three with a one and a two, and possibly even some larger sums, although they're going to be much less of a consideration in this particular formulation. So, right, so if there's a three, I can't play a one, two sequence either before or after that. And so the best thing I can do here is alternate between threes and ones, right? So, I mean, this assumes I put a three somewhere. If I never use threes, I can go back and forth between one and a two. But once a three is there, I can't put one and two next to each other or else there'll be a slap. So to avoid that, kind of the best thing I can do is just have a three in every other spot and put ones and twos surrounding that. But I also don't want to have, say, two twos in a row. And by in a row, I mean something like 3 2 3 2, because that would also cause a slap because the 3 2 would match with the next 3 2, both summing to 5. And so I want to alternate between 1 and 2 as best I can, right? So something like 3 1 3 2 3 1 3. And then when I get to that last two, I actually have to slap because here that 3 1 3 2 at the end, right? That sums to 9. And that will match the first four digits, which also sum to 9. So are the lessons in either of those for four cards? And surprisingly, I mean, there are a couple, but not as many as you would hope, right? So it helps you kind of maybe think about the rules and clarify exactly what you need to do. But but the trick of this puzzle, the thing that makes it so hard for me to figure out what kind of the point of it is or how you're supposed to solve this in a meaningful way is that everything just seems so specific to a particular set of numbers or to a particular kind of arrangement. Like it's very hard for me to think of a way to generalize how this process would work of finding the longest chain. And see when I get to five or more, which we'll do in the extra credit, I'm just going to resort to code and doing an exhaustive search for the types of patterns because I don't really see what you can do besides recognize some things to avoid and some kind of big picture patterns. But guaranteeing that you've maximized the number here just seems incredibly hard without an exhaustive search, given the things that are involved. So before I resorted to code, I kind of thought about two different approaches here. So one approach is, and this is not the first approach I tried, but I think is a useful first approach to think about, is to think about putting a four in that optimal sequence we had before, right? So we had a sequence of the cards between one and three, and is there any way I could put a four in there and extend the chain? And it actually turns out the answer is no. Right? So there are four different ways to maximize the length of or the size of the pile in the terms of the game. And it's something like 1 3 2 3 1 3 2. That's one way you can maximize it. And then from here, any other number you put down is going to result in a slap. So there's no place I can put a four here, right? So why can't I put a four here? Well, where am I going to put it? I can't put it next to a 1 3 chain. So putting it at the very beginning is out. Putting it between a 3 and a 2 is out. You might think, well, can I put it between a 3 and a 1? Will that work? And it turns out that doesn't work. It depends where you want to put it. If I put it next to a 1, like let's say here, then that 4 and the 1 will add to 5, just like the 3 and 2 after it, right? So that's a problem. Same thing over here. If I try to put it toward the end, then what I'm going to end up with is a 3 2 4 summing to 9, and that's going to be preceded by a 1 3 2 3, which also sums to 9. So there's no place to put it here. 2 3 1 3 2 3 1 is another way that I can maximize this, but this is just the mirror of above. And so, one thing that's actually interesting to note here is that forwards and backwards in this chain doesn't really matter. It may seem like it matters because once you put down a card, you don't have to think about numbers beforehand. But if I play cards in a certain order, doing them in the exact reverse order also will have to be valid, just by the way that math is going to work out. So doing the exact mirror will also work, but because it's mirrored, the exact same logic is going to tell me that I can't place a 4 anywhere here. I could do 3 1 3 2 3 1 3. The problem here is there's just no place to put a 4 that escapes putting it next to a 3 1. Or I guess I didn't write this down, but or next to a 3 2, right? If I put it between this 3 and 1, then 4 and 1 will be next to each other with a 3 2 following, and that will both sum to 5, and you end up with an early slap. Or the last way to do this maximally is 3 2 3 1 3 2 3. And just like basically for the exact same reason that the first one doesn't work, these don't work, right? You're either going to run into 3 2 next to 4 1, you're going to run into 4 next to 3 1, or we're going to run into 3 2 4 next to 3 1 3 2, both summing to 9. And so basically recognizing those patterns, right? 4 1 next to 3 2, 3 1 next to 4, right? 4 3 2 next to 3 1 3 2. That's eventually how I ended up trying to get at what I think is the largest maximal chain. But that's not very satisfying. So I want to think a little bit more about how you might construct this in a more general sense. So this is what I call approach 2. So like with the 3-card example, right? How do we get the maximum possible chain? I wanted 3s everywhere, and kind of at every other number because you can't repeat them, and then alternate between 1s and 2s. And so maybe if you just put 4s everywhere, that'll help. And there's an intuitive logic to this, right? So if you think about this from like a probabilistic standpoint, the larger this number is, the less likely it's going to be that two kind of sequences of digits are going to end up having exactly the same sum. In other words, sum. Another way of thinking about that is if I put a large digit somewhere in the chain, that kind of extends the length, the distance between the sum of the previous numbers that doesn't include that digit and the number that does include that digit, right? So ones in this case are actually quite bad because, um, like, if I have two sums right next to each other and I put a one on one side, well, if they weren't equal before, it's possible that I'm going to make them equal again because, like, let's say I have a four and a two, right? So I'm going to six, and before that, it's next to a five, right? Well, that five is smaller than the six, so to see if this condition is met, I'm going to check the next number in the chain next to that five. And if it's a one, that's just going to bring it to six and make it equal. And if I put a bigger number there, I'm going to jump from five to a larger number than six. And I'll kind of skip over the six and allow the sequence to continue. So the larger these numbers are, the more likely it is that I can kind of keep leapfrogging back and forth between large sums, or between the sums of the the numbers connected to the final card and the previous numbers. And so large numbers are kind of good in that sense. And so, putting fours everywhere seems like a pretty reasonable thing to do. So, as an example, I might go 4, 3, 4, 2, 4, 1. But the problem here is I'm going to slap on that one because 4, 2, 1 adds to 7 next to a 3, 4, which also adds to 7. So this isn't even as good as the case without fours at all. So I can't just kind of haphazardly start with fours and put 3, 2, 1 kind of alternating down this chain. So can I change the order of this somehow? It turns out no, right? I can't really just change the order of the 1, 2, and 3 and make it work. Even if I try to start with 1, 2, or 3, that's also not going to work. Basically, when I get to the sixth number or so, I'm going to slap, and that's not going to work very well. So, so, and when I started thinking through this, I thought, okay, if I have alternating off digits with the fours, then I'm definitely preventing two-digit sums from matching. Right? I'm definitely doing that well. But with these fours in here, these one, two, threes, there's just so many ways to come up with either two, three-digit sequences or two, three-digit sets to be equal to each other, or three-digit and two-digit, right? There's so many ways for these numbers to combine in a way that will result in equal sums. And so you can't just kind of systematically go, okay, well, 4, 1, 4, 2, 4, 3, or there's no systematic way of looking through this. You need to be a little bit more careful about what you use in your off positions. And this gets back to the idea that I talked about earlier, which is high digits are good in the sense that they increase the distance between your sums. And so they make it less likely that your sums will end up matching. And so one thing I might do is try to maximize when I can do three. So for example, I might do 4, 3, 4, 2, 4, 3, 4, 1. And then when I get to 4, I slap. So what am I doing here? I'm starting with 4, and I'm alternating 4 every other digit. And I'm using 3 when I can't use 4. And the fourth digit, I put a 2 because I can't use 3 again because that'll just have a 4, 3 followed by a 4, 3. I don't want to repeat the same digit pattern. I'm going to put a 2 there. But then I'm going to go back to 3. Rather than going to 1, I'm going to go back to 3 because, again, 3 kind of maximizes the distance that I'm putting in here. And then back to 4. And now I can't do 3 because that's going to repeat the 4, 3, 4, 3 pattern. I can't use a 2 because that'll do 4, 3, 4, 2, 4, 3, 4, 2. So I'm going to go down to 1 finally here. And then it turns out once you put that 1 there, anything you put after this is going to result in a slap. But this is a little bit better than without fours at all. I have 8 cards that don't result in a slap in a row. And we only got to 7 in the 3-card version. But we can do a little bit better here. So one thing you might notice is that this pattern is somewhat symmetric, right? So if I ignore the last one, 4, it's actually exactly symmetric. I have 4, 3, 4, 2. 2 is the center. And then it goes back the same way, 4, 3, 4. And when you put that 1 there on the right, it doesn't create a slap. And by the logic we talked about earlier, where mirrors are kind of the same thing, then putting in the one on the left, if I didn't have this one here, putting a one on the left also wouldn't cause a slap. So I could put a one there on the left, and it's possible that if the two ones kind of interacted somehow, then there might be some kind of slap possibility. But because this particular set of numbers, before you include this last one, four is of odd length, there's not going to be an interaction there. Whereas if it were an even length, it might. But anyway, by placing a one on both sides, I can actually make this a little bit longer. And this ends up being the unique kind of set of digits that will maximize the number of digits I can play, the number of cards I can play before a slap will occur. After this, any card you play is going to result in a slap. Now, how do I know it's the largest? Because, we can talk about this kind of, it's not even theory. It's just, we can talk about these intuitions behind it. But if I actually want to prove that there's no way to do it better, I don't know how to do it. So I just did an exhaustive search through code. And it turns out that this is the best way to do it. That there is nothing better with four card types. So, and again, if you have a better way, if you can think of a way to prove this without resorting to an exhaustive search, I would love to hear about it. And so going into the extra credit, for four types of cards, I can't do it without an exhaustive search. I knew there was no way I was going to do it for, more than that. But the basic question for the extra credit is, what if you had five different types of cards? The numbers 1 to 5, 1 to 6, 1 to 7, right? How would that change your answer? And doing this again through code has only cemented my belief that there really isn't a good analytical way of approaching this. I mean, there are just so many different things to consider that I don't know how you could possibly do this without an exhaustive search, right? And it turns out by looking at the sequences that emerge as the kind of optimal ways of going about it, there just really aren't many patterns. You have to be pretty careful about how you place digits. And there just really isn't a good obvious pattern, right? So I don't always want to maximize digit size the way I did in that 4342 example, right? They don't end up being symmetric all the time. In fact, most of the solutions here are not symmetric. They aren't even unique, right? So for the 5 case, there are just so many possible ways to get to the maximum number. And there doesn't really seem to be any common thread amongst them, except that they all kind of rely heavily on 5s and 4s. But exactly how they're placed, exactly how they go, it just is so different and varied that it makes me think there just isn't a good way of approaching this that isn't just exhaustive. So to give you an example for this, here are 2 different examples for n equals 7. So here's one longest possible chain of digits you could end up with. This chain will not result in a slap at any point in the sequence. Now compare that to this other sequence, right? This first one happens to be the kind of smallest possible sequence in terms of, like, if you did a search, if you put all these digits together as if it were a single number, right? So I think it was 31 digits here. I'm not going to count them right now. But if this was a 31 digit number, this would be the smallest version of that. But the second one is just a random one I chose. And again, other than having lots of 7s, right, but not always 7s, right? If you look at this first example, here I have 7, 6, 7, 5, 7, 6. I mean, that seems like it's kind of following the pattern, but now I add 4, 3 in there. Why don't I go to 7? And then you think, well, 4, 3, 3, 4, or 4, 3, once they kind of once you get away from that, they act just like a 7. So why not replace all the 7s with 4, 3? Shouldn't that make the sequence even longer? Well, sure, except that if that 4 or 3 results in a slap either here or further up the chain, rather than that 7, then it's not going to work. And so why would you use a 4, 3? When would you use a 7? It's just not obvious to me at all why that would happen in this particular pattern. And same thing down here. In the second sequence, again, you have lots of 7s, lots of 6s, a good number of 5s, but it's just not at all clear to me why you would end up in this exact arrangement other than it just happens to work, right? It just happens to work when you go through the sequence. Um, and so it turns out that there are 22 different ways to reach this thing. Now remember that um, unless the pattern is symmetric, which most of them are not symmetric, any like this example up here is not symmetric, which means the mirror of it also works. So instead of 17675, I could do 675764, etc. That's also one of the valid patterns. And when I say there are 22 ways to do it, I'm including those mirrors in that count. So I don't know exactly how many of them were symmetric, but basically there are somewhere between 11 and 22 kind of really unique ways of doing this. And it's, the really weird thing about this is I mean, all of the sequences have one somewhere in them, but of those 22 ways, there's only one that has a two at all. And that one has two twos that are in kind of symmetric places. So it is, it's not clear at all to me why two is special, and this doesn't apply to the puzzle when you have five different kinds of cards or six different kinds of cards. Like for some reason, with seven cards, two is just really unlikely to end up in this optimal sequence. And I think it's just one of those situations. Like I understand why two is generally bad because it's small, but why does one show up so often, right? And not two? And that's just something I don't have a good intuition for. And if you do, again, please let me know. And just a final wrap up, just to tell you what the answers are from the code. And I'll post my code and an Excel sheet with all the exhaustive sequences that maximize the extra credit. So if you have five different cards, then you can get 15 cards placed before you have to slap. And there are 111. There are 111 different ways to get to that maximum length, which is just astounding, especially when you compare it to when there are six cards, right? You can get to 21 digits in a row, but there's only five different ways to do it. So there are way more cards, way more possible unique sequences, but only five of them work. Whereas in the shorter sequence, you get a bunch more that work. And when you go up to seven, so it's not like this is even some type of monotonic. I mean, it's monotonically increasing, of course, in the length of the chain because, there's no way it can decrease because at worst case scenario, you just wouldn't use that last card that gets added. But the number of ways to do it just kind of jumps around all over the place in a very strange pattern that I don't really understand. Again, if you do, please let me know. Very interested to hear. But that's it. That's all I have for this puzzle. Hopefully you had a little bit more luck than I did trying to find some meaning here. All right. Thanks for watching. I'll see you next week.